Alrighty, this is going to be the last discussion in chapter 27, and we'll move on to magnetism, and we'll pretty much finish the course in next 2 weeks on chapters 28 and 29. Anyway, what we're going to look at here is a what's called an RC circuit. This is a resistor capacitor circuit. It's the first time we've seen capacitors in the circuit itself, and so what we're gonna look at then is the following seemingly simple circuit. I'll draw it as your book does, so I'll use figure 2715 to open up the discussion, but then I'll draw two circuits from this that will simplify the discussion. So if we imagine we have a source of EMF, electromotive force, positive, and what we're going to have here then is a circuit that looks like this. So here we're going to have a switch, and that switch can toggle between positions A and B, and then we're going to have a resistor in series with a capacitor. Okay, so it's a resistor, capacitor, and this switch can toggle back and forth, as I said, between positions A and positions B. So when the switch is toggled up to position A, then the electromotive force will be part of the circuit. So when switch S is toggled, I hope that's spelled right. Let me just check on. Yep. So actually, what we're going to do here is correct that. So when the switch S is toggled to position A, the EMF is part of the circuit, and the capacitor will charge up. Okay, and then when the switch is toggled to position B, the EMF is not part of the circuit, and the capacitor will discharge. So let's look at these. Let's look at these two parts of this circuit, right? So let's look at the charge up scenario, and we'll look at the discharge scenario separately. Okay. So let's begin to do that. So here's the circuit then. Looking at just the charge up. So we're going to have our resistor, our capacitor in series. Resistor, capacitor. We're going to have a switch here. So before we close the switch, there's no charge on the capacitor, obviously no current in the circuit. Okay, so we're going to now close the switch. Let's close the switch. Switch is closed. And now the circuit is complete. And we're going to have a current. A current which moves through this circuit. But please be aware that that current is going to be a function of time. It's not going to be constant. Because once the capacitor charges up to a voltage such that no more current will flow, no more charge will flow, then the current will go to zero. What is that voltage? That voltage is when the voltage across the capacitor is equal to the EMF. Okay, but let's formalize this. So we'll use Kirchhoff's voltage law. And so going around that circuit, starting at the low potential side of the EMF, charges will experience a voltage gain. As the current goes through the resistor, there's going to be a voltage drop across the resistor. And there's going to be a voltage drop across the capacitor. And that will be equal to 0. So, so if we look at this now, the voltage across the resistor is going to be the current flowing through it times the resistance. The voltage across the capacitor is going to be the charge developed on that capacitor as a function of time divided by the capacitance. So then we have EMF minus I as a function of T times R minus Q as a function of T over C is going to be equal to 0. Let's recall that the current is equal to the time rate of change, or the first derivative of the charge. And consequently, then we could make that substitution into Kirchhoff's voltage law. So we will have then E minus dq dt minus Q over C is equal to 0. And keep in mind that Q is a function of T, but I'll stop writing that so that the equation looks a little bit more streamlined. And I'm going to rewrite this in the form that one normally sees it. So this is dq dt. I forgot R in here, so there's an R. There we go. Dq dt times R. Plus Q over C is equal to E once we take care of the negative signs. And so this now is a first order differential equation. It's an equation that contains derivatives, so that's why we call it a differential equation. It's first order because it only has a derivative, a first derivative. So the solution of this is not exactly straightforward at this level. There is a proof of it in your text, and for those of you who are interested, can look on page 791. Look at page 791 for Halliday, Resnick, and Walker. But let me just rewrite this. So this would be dq dt plus q over rc is equal to e over r. And so the solution to this differential equation then is going to be q as a function of t is equal to c times e, 1 minus e to the negative t over rc. Okay? And we can distribute in the c times e, so this is going to be c times e minus c times e to the negative t over rc. Now this tells you how charge is going to build up on the capacitor as well. Okay, we'll explore that in a second. Okay, so the current now, if we were to look at the current as a function of time is going to be the first derivative of q with respect to t. E and c are constants, so that will give you 0. And so then this will be negative c times e. This will be negative 1 over rc, e to the negative t over rc. The c's will cancel, and then this becomes e over r, e to the negative t over rc. So that's going to be the current as a function of time. Now, if we were to plot that out, so here's time, here's the current, and so now when time is equal to 0, then e to the negative t over rc is equal to 1, and so the current now is going to be equal to e over r. So here it is here. This is going to be e over r. And then this equation is going to exponentially decrease over time. And so that's going to decrease exponentially over time. So this is going to follow an e over r, e to the negative t over rc, functional dependence. And we know that arguments in exponentials need to be unitless. And so t over rc must be unitless, which implies then that rc has units of time, or in SI units, that would be the unit of the second. Okay, which is kind of interesting because we know that resistance has units of ohms, and capacitance has units of charge per unit voltage. And I'm going to leave that up to you, right, to prove that that combination, that product, actually results in units of seconds. Right? This is for you to show. Okay? Beautiful. Now, likewise, we can look at the charge. We can look at the charge buildup on the capacitor, charge buildup on the capacitor, and so then that's going to be Q of t is going to be equal to CE. We'll write it back this way. It's going to be CE. 1 minus e to the negative t over RC. And if we just look at this at its extremes, so at t equals 0, e to the negative t over RC is equal to 1. And 1 minus 1 is 0, and so Q sub t at t equals 0 is going to be 0 coulombs. At t approaching infinity, e to the negative t over RC is going to approach 0. And so then Q of t is going to be equal to C times E. In between, so if we look at plotting Q of t as a function of t, then we know it's going to be 0 at time equals 0. And we know at very long times it's going to approach C times E. And so that's going to look something like so, with the functional form in between C times E, 1 minus E over T times RC. Okay? Beautiful. One can also analyze the voltage across the capacitor. The voltage across the capacitor then is going to be Q over E in this case, the voltage that's supplying the voltage supplied by the EMF. This then is going to be Q sub t over E, which is then is going to be C times E over E, 1 minus E to the negative t over RC. At t equals 0, then e to the negative t over RC is equal to 1. 1 minus 1 is 0. And so then the voltage across the capacitor then is going to be 0 volts. At t approaching infinity, e to the negative t over RC is going to approach 0. And so the voltage across the capacitor then is going to be CE over hang on here, what did I do? Voltage across the capacitor is Q over C. Yeah, my bad, guys, right? So this is going to be Q over C. Yeah, Q over C. There we go. Now we're good. So that's going to be then CE over C. C, and those cancel, and it gives you E. So the voltage across the capacitor will ultimately be equal to the EMF value. All right, beautiful. We have the discharge, and I guess I'm approaching my time limit here, so I'm going to look at the discharge in the next part. Okay, talk to you soon.